Hey, good afternoon, everyone. Welcome to my wel- welcome to my channel. And in today's video, what I will be going on is I will be covering chapter two, and chapter two is basically mostly covers fundamentals of Ethernet. And when we talk about fundamentals of Ethernet, referring to OSI model, we'll be focusing more on layer one and layer two. And of course, on layer one, that's where your physical connections lay, right? So we'll be going over uh, fiber cable, straight through, crossover, and of course, different standards, uh, different LAN standards. So your local area network, and what are some standards that you'll end up implementing depending on your topology. So, of course, your 10, 100, 1,000, and 10 gig standards. We'll dive deeper into each standard, their names, and the limitations. Also, we'll be going into MAC addresses and also different addresses. So your broadcast, unicast, and multicast. So let me add that really quick. So your group addresses, which are going to be your multicast and broadcast. Let me give you just a second if I can type this correctly. And your unicast address. Then we'll be diving into a little bit in detail for frame, um, more into inspection, more diving into different fields that are in the frame, headers and trailers. And of course, we'll be going into SFP module. So these modules that go with your modular switch, your GBIC, SFP, SFP plus, and at the end we'll be covering half-duplex and full-duplex. And of course, those of you know who have duplex, it comes with collision and the algorithm that goes behind it to avoid collision in the environment, which is your CSMA CD, which stands for carrier, which stands for carrier sense multiple access with collision detection. So, so quite a few topics, and once again, these are the topics that they'll help us build foundations as we progress along from chapters to chapters. It will really help us build a foundation, kind of like build a base. Um, so, uh, let's dive deeper into the chapter. Let me scroll up. I was just taking notes while I go, but once again, any questions that you guys might have, feel free to put them in the comment below, so that I can always go back and help you as much as I could. And once again, my main goal is to share all the resources that I'll be using towards my CCNA exam. So hopefully this will help you. This will help you aside from what you already are using, or at least help you, uh, you know, build as a good foundational resource going forward. So let's dive deeper into the chapter. So the very first topic that I have right now is the SOHO. And what SOHO is basically, it stands for small office, home office. So your small office, home office environment will typically, back in days, of course, will look like just a switch or a hub, your router that gives you access to the internet, your end user devices, which are going to be your workstations and printers. So very basic topology. Um, uh, back in days, but as we all know, in today's environment, you just have more than, it's not just your workstations, correct? You have your tablets, you have your IoT devices, you have your server environment. So it's more complex and complicated, but this is just to understand your basic uh, fundamentals on what small office, home office looks like. Moving further, so of course, SOHO stands for small office, home office, and you might be wondering what the topology will look like in small office and home office. So once again, we have from time to time, as we have advanced into technology world, well, you can tell that it's not just workstations and printers. Now, on this specific example, we have access points, which provide wireless connectivity, and you have your tablets and your end user devices that connect to it. Um, Once again, this can be access point, this can be a wireless LAN controller, so it can be many things. What your typical enterprise three-story building will look like. So, this is your three-story building, and of course, it can be just more than one building. You might have a campus where you have more than one buildings, depending uh, depending on your environment. Once again, but in this specific example, Cisco goes over a three-story building where you have uh, each floor in its own network segment. So you have your switch, you have your printers, you have your access points, um, and your workstations, of course. So just by looking at it, you can tell that each floor has its own switch, and they all go to the back end switch, or you can call it as a main switch, or if you want to call it like a core switch. So all your connections go to the core switch, and the core switch has a connection that goes to the router, which will provide them access to the internet. So I know those of you who don't know, but those of you know, it's great. Cisco has a different architecture. If they have like access, distribution, and core, like a three-layer or three-tier architecture. And once again, this is just a very uh, basic example, just to understand or how a typical enterprise will look like. Going further, once again, as I mentioned earlier on the list, we'll be covering IEEE standards. Once again, IEEE standards play a critical role in the environment. So depending on the environment that they work, maybe it might be your or company's location, or it might be client side. You need to understand the standard that's being implemented, right? Let's say you might have a customer or a client that you work in a project that has a thousand gig, thousand base Alex standard. So you need to understand, because standards will create like a foundation, and then and on top of standards, that's where you have all your protocols that be running. So diving deeper into Ethernet standards. So IEEE is the one who defines standards, who defines Ethernet standards, and your protocols are defined by RFC. This is something that I always had trouble understanding going into these Cisco exams. Is that RFC stands for request for comments, and they are the if you look at the request for comments, they define protocols. They define how protocols should work, and IEEE stands for Institute of Electrics and Electronics Engineering. They're the ones who define Ethernet standards. And when you look at Ethernet standards, we have different types depending on the speed. So you have your 10 megabits, which is Ethernet, and base T, 802.3 uses copper, and it's limited to 100 meters. Then you have your 100 megabit connection, which has a name of 100 base T. It has a standardized name of 802.3U. It uses copper. Then you have your 1000 megabits per second, which is your 1 gig connection. And if you look at the name, it has 1000 base LX. And the IEEE standard name is 802.3Z. And it's a fiber connection that has 5,000 meters. So just by looking at the table, you can tell that you can tell the differences, right? It's like, hey, the fiber has longer distance than copper, because with the copper implementation, you're limited with you limited with the distance, so you can go further if you want to, with having a copper cable. But at the same time, those of you know, copper is much cheaper than fiber cable. So when it comes to the environment, for shorter runs, you probably end up using copper, but for longer runs, you will see fiber link connections coming uh, into the switch or router, or whatever device that you have plugged in. So just where I left off, you 1000 megabits per second, 1 gig connection, 1000 base T, 802.3 AB, which is copper, 100 meters. Then you have a 10 gig connection, which is 10 gig base T, 802.3 AN, which is copper, 100 meters. So your T stands for the way going into the exam. I know there's a lot of memorization that will go into the CCNA exam. You know, just go into the questions. They might end up asking you a question in the exam where like, hey, we have a enterprise building. Let's let's just say let's just make up a question really quick. Let's say we have an enterprise building. Uh, you know, it has a speed of 1,000 megabits, 1 gig connection, and the distance needs to be 4,000 meters. So just by looking at you being as a network engineer, you need to make sure that you have a right standard that's in place. That's compatible and that works with the given requirements. So in this case, your 1,000 base LX will be that's the standard that you'll be using in your environment. So of course it's going to be your fiber connection, and your distance is going to be up to 5,000 meters. So please do keep in mind this table is going to be very, very important going into the exam. And those of you who are registering for CSENT and CCT, you will be tested on this. So you can go ahead and take a screenshot, take a picture, pause a video. It's up to you, whatever is easier for you. But please do keep in mind that you will be tested on this. Going on the right side, just a second. That's where I have all of my notes. So going on the right side, um, what I have from referring to Cisco's official study guide is that your Ethernet link refers to any physical cable between two Ethernet nodes. And of course, your Ethernet link. This is something that you will see a lot in the exam, and it's just a term. To just don't let it get confused. Just trust me. As we make further progress into this Cisco exam topics or different chapters, there's a lot of learning that will go with it. So a link is basically just a connection between two devices. So if someone says, "Hey, Ethernet link between printer and a switch," PC between switch, or switch between access point. So that cable or the connection right there, that's going to be your Ethernet link. And also, an important note, very, very important, is that the 10 base T and 100 base T uses two pairs of wires. And once again, we will dive deeper into what I mean by two pairs of wires, but just have this important note that the 10 base T and 100 base T uses two pairs of wires. All right, moving further, as I was talking about SFP modules, um, that's one of the exam topics that will be tested upon. That will be tested on is that you have your different modules into a switch. Depending on the switch, some switches are modular, some are not modular. Um, but but if you look at the older catalyst switches, the one that I use that I see have some 2900s, they usually have a modular on the right side of the switch, and the location would depend, but usually they're on the right. Um, where you can have like a small form pluggable transceivers that you can plug in uh, for connections. And let's say if we have a switch that only supports 10 and 100 megabits per second, and let's say you need an uplink, or you need or you need a gigabit link that goes from your access to the core switch, or to the distribution switch. So in that case, these modules will come in handy because all of your ports only support 110 megabits per second. So what you can do is you can buy one of these modules. You can just plug it in, and now you have a gigabit connection that goes into your fast Ethernet or Ethernet switch. So as you can tell just by looking at the picture, GBIC. GBIC stands for Gigabit Ethernet Interface Converter. Wow. So just by looking at the picture, you can just tell that it's quite bulky. It's kind of like the size of a credit card. and it's a little bit thick too. So JPEG is the very first original form factor that was launched, or that that came out. So it's the very very first one, and then they came out with SFP and SFP plus. So just by looking at the key differences, is that SFP, they look like a flash drive, and trust me, those of you have seen it, they are quite the size of a flash drive. But they're a little different. But just by telling, just by looking at the key differences, is that GBIC ends up taking a lot of space, whereas SFP requires less space, and does the same amount of work than what GBIC does. So going back to the notes, what GBIC stands for is Gigabit Ethernet Interface Converter, and it is the original form factor. So the very first one to come out. And it is for a removable transceiver for a gigabit interface. So this will create a gigabit. This will provide you with gigabit interface for a gigabit link, and they are larger than SFPs. Then going forward is you have SFP plus, and SFP plus, which is right here on the left. They're replacement of GBICs used on gigabit interfaces. They're much smaller size, and they take less space on the switch, which is a good thing, right? If you have less space on the switch, now we can fit in more hardware components, uh, uh, components in the switch that will give you more features, with the same amount of work that you want to do. So they really dominated. All the newer switches, they have SFP connectors now. So JBIC, you may end up seeing one depending on the switch, but mostly you will see SFP. Then you have SFP plus, small form pluggable plus, which is the same as SFP, but they're used for 10 gig interfaces. So if you have a 10 gig connection, it won't work on SFP, but you need to buy SFP plus module. And also, 10 gig has their own different standards. So depending on the standard, so when you end up buying an SFP plus module, you need to make sure you get the right one, because they all have different standards in 10 gig. There are different standards in 10 gig connections, which we'll see later, in this chapter. But it's something that that will make more sense as we dive deeper into it. All right. So as I mentioned earlier, or as those of you remember, is that while we were going through different Ethernet standards on the top, um, while we're going through different standards, I left a note where it says that the 10 base T and 100 base T uses two pairs of wires. And what I mean by that is if you look at this logical connection of a cable between a PC and a switch, you will see two pairs of wires being used to send and transmit data. So on the left, you have your straight through cable. Uh, on the left, you have your I'm sorry. On the left, you have a PC, and on the right, you have a switch. So for this sake of the chapter, what I will be going over is that um, is the straight through connections. And when you think about straight through, there are different types of cables that are being used between devices, when you connect different devices. So in this case, when you have a PC and a switch, you'll end up using straight through cable, which means that they're used when you're pairing unlikely devices. So in this case, you have two opposite devices that you're trying to connect. You will use a straight through cable. So what your 10 base and 100 base connection will look like: two pairs. So your one pair will send the data the other in one direction, and the other pair will send the data towards the other direction. So in this case, your PC, or if you see the pins, because your RJ45 has total of 8 pins. Let me see if I can pull up a RJ45 cable. So this is just I took it from Google, but if you have a CAT cable or RJ45 cable laying around, and if you look at the pin connections carefully, you have total of 8 pins, correct? So, and straight through cable, you have your pins 1 and 2, which will connect to 1 and 2 on the other end, which will create one pair. Then you have your 3 and 6, which will connect to 3 and 6. So your one end, or your PC, let's say in this case, will transmit on 1 and 2, and your switch will receive at 1 and 2. And once it processes that data that came through, the switch will transmit at 3 and 6, and the PC will receive at 3 and 6. So the way that I remember going into the exam once again is that your straight through are used when you have two unlikely devices. So in this case, you have a PC and a switch, or it could be a PC and a hub, or it could be a server and a switch. And if you look at the pins, you have 1 and 2, which are connected to 1 and 2 logically, and of course you have 3 and 6, which are connected to 3 and 6. One end will transmit, the other one will receive on the same end, and looking at from the receiver side, it will transmit on 3 and 6, and the other end will receive on 3 and 6. So your pins do not change. Your pins are same. And once again, it will make more sense once you look at the process. So in the bottom, this is a good visual presentation uh, of what connections will look like. So in this case, you have a Larry, which is a PC, and you have a RJ45 cable plugged into its Ethernet card going to the switch. So Larry will send data. First, what Larry will do is Larry will create logical connections. So at 1 and 2 and 3 and 6. So those are your two pairs, correct? Remember, two pairs. The one pair is 1 and 2 to 1 and 2. The other one is from 3 to 6 to 3 to 6. So that those are your two pairs going into the exam. So your 1 and 2 will transmit, and the other one will receive at 1 and 2, and you have your 3 and 6, which will receive, and the other end will transmit. So please do keep in mind, just by looking at the picture, is like your pins, they make connections on two same ends. So your Larry makes connection on 1 and 2, and on the other end on the switch at 1 and 2, and 3 and 6 and 3 and 6. So please do keep in mind going into the exam that your pins are 1 and 2 to 1 and 2, and 3 and 6 and 3 and 6. If one end transmits, the other end will receive. So in this case, 1 and 2 will transmit, it will receive at 3 and 6. So it's flipped for switch. That's the way that I remember going to the exam. Now, moving forward into crossover cable, your crossover cables are used when you have two same devices. So in this case, by looking in the picture, if you're trying to connect switch to a switch, you'll use a crossover cable. Or let's say if you're trying to connect a switch to a hub, you will use a crossover cable. Okay, sorry about that. Just grab some water really quick. So your crossover cable are used when you have two same devices in the end. In this case, you have a switch. Once again, when you have a switch on both ends that you're trying to connect. You use a crossover cable. But with the crossover cable, look at the pin management. Your pin management is different than what you would have typically. So on straight through, your pins were connecting from 1 and 2 to 1 and 2, and from 3 to 6 to 3 to 6. In this case, you have pins 1 and 2. They connect to 3 and 6. So you can tell that they are flipped. They're flipped from the other end. In this case, once again, just trying to compare two different pictures so you guys can understand the bigger picture. Is that 1 and 2 connects to one end, and it also makes a connection at 1 and 2 on the other end. But in this case, it will make a connection at 1 and 2 and 3 and 6. So one of the end, the pins are flipped. So in this case, 1 and 2 will transmit. It will receive at 3 and 6. So 1 and 2 will transmit. It will receive at 3 and 6. And I'm sorry, yes, 1 and 2 will transmit. It will receive at 3 and 6. And it will send data at 1 and 2. And it will receive at 3 and 6. I know it kind of sounds confusing, but I have a better picture, or I have a better visual that will make it clear. So on the top, you have a straight through. Your 1 and 2 is connected to 1 and 2. 3 and 6 is connected to 3 and 6. One end will transmit, which is right here, and the other end will receive. Same thing going to the other direction. That's for straight through cable. For crossover, the pins are connected differently. So it's connected to 1 and 2, to 3 to 6, and the other end is connected from 1 and 2 to 3 to 6. So you can tell the pins are flipped. So one end will transmit, the other one will receive. Same thing, it will send the data from other way. So hopefully this visual will help you understand the logical differences on how straight through and crossover cable work. But now, those of you who have already done some cabling or implementation in IT environment, you'll be you will be you'll be asking me like, hey, I never I never ended up using two different cables into the exam. Just give me a second. I'll be right back. Okay, sorry guys. Just had to step out really quick. But going back where I left off is that to get my charging cable from my laptop. But going back where I left off is that the way going to the exam to remember is that your straight through and crossover cable, the connections are flipped on both on one end, and also those of you who already worked into the in real life environment, which could be your data center, could be done some cabling work. You might be wondering, you might be asking like, hey, I never ended up using two different cables, right? I never ended up using two different pairs of cables. I only use that cable. I plug it in and it works. The reason why it works is because Cisco has a feature called Auto MDIX. I mean, it's not just Cisco; it's mostly every other switches from different vendors that has a feature called Auto MDIX, which means that it will automatically change the logic connection. And what I mean by that is, let's look at the topology really quick, and it will help us understand um, how it works. So now we know that the straight through cable is used between two when you connect two opposite devices, right? So when you have a PC and you're trying to connect it to the switch, or when you have a server or a printer that you're trying to connect to the switch, you'll use a straight through cable. And when you are connecting two same devices on both ends, you use a crossover. In this case, for this example, just by looking at the topology, when you try to connect connections between two switches, you will use a crossover cable. Now, going back, going back to answer your question, or those of you who are surprised, it's like, hey, I never ended up using two different pairs of cables. I was just plugging in the cables as I go when I was implementing, when I was doing infrastructure work. The reason why it worked and the reason why you're not using two separate pairs, two separate cables, is that it's because one end is because of this feature, Auto MDIX, where let's say if you ended up using a let's say if you ended up using a straight through cable, and once again, the use cases for straight through cable are when you're trying to connect two opposite devices. So in this case, when you're trying to connect switch to a PC, in that case, that's where the straight through cables are used. But let's say if we ended up using straight through cable between two switches, this is where the feature well, this is where this is where the feature will automatically come in and do its work, where where it will detect that the wrong cable is plugged in, and it will automatically change its logic to make the link work. which means that it will logically change the connections once again. So let's say in this case, you plug in a straight through cable between two switches, and once again, if you remember how the pins work in straight through, is that you have your 1 and 2 and 1 and 2. So 1 end will transmit, the other end will receive, and 3 and 6 and 3 and 6. But crossover is a little different because your crossover it's flipped, right? So let's say if you ended up using a straight through cable between two switches where you're not supposed to use it, this feature will automatically change the pin, will logically change the connections to make it work. But for the exam, please remember that they will test you on use cases between straight through and crossover. So it's also good to know about this feature that that switches have, but also but like once again, Cisco will focus more on foundation, so you will need to understand the two differences between the cables. And once again, if you guys have any questions or if you guys are confused, I'm more than happy to answer all of your questions. And just leave a comment down below. I know it's not perfect, but anything that I can help you with, um, please do. All right, moving on to Gigabit Ethernet, and those of you, um, not those of you, but going from our previous going from our previous notes about 10 base and 100 base T, where they use 4 pairs of wires, 1000 base T. Sorry, 2 pairs of wires. 1000 base T, which is a 1 gig connection, uses 4 pairs. So it's not only 1, 2, and 3 and 6 now. It's 1, 2, 3 and 6, 4 and 5, and 7 and 8. So please do understand these differences, because while I was going through some CSN practice exams, they did at one point there was a question where one of the answers was, hey, 1000 base T uses 4 pairs, and 10 and 100 base T uses 2 pairs. So please do keep in mind, and I'm gonna scroll up really quick, and just tell you differences, right? So this is your 10 and 100 base T. You have your 1 pair, which is 1, 2, and the other pair is 3, 6, right? And but like in 1000 base T, now you have 4 pairs, so it's not just 1, 2, 3, and 6. It's 4, 5, 7, and 8. So please do remember going into the exam. All right, now let's jump into some fiber cable. Oh, I have that as a note, but let's just jump into fiber cabling. Your fiber cabling, once again, when we were going through the IEEE standards, we real some of you might already some of you already have a background. They probably know by now that fiber it's usually used for longer distances, right? They're expensive, but the technology behind the fiber is different than what you see in the copper. So what fiber uses light to transmit. And when you look at the underlying structure of a fiber cable, there's a different engineering that goes with it. So, looking inside the cable, you have your diving deeper into the components of a fiber cable. What makes up the fiber cable is that you have your outer jacket as a protection. Then you have a strengthener. Then you have a buffer, and then you have a cladding and your core. And just by going by the name of core, you know that's a critical part inside fiber, right? So, you know, going into the exam, these are the key notes that we need to keep in mind. Is that there are 3 outer layers that will protect the cable. So your outer jacket, your strengthener, and your buffer. Those are the 3 outer those are the 3 outer layers that will protect the cable. And your 2 inner layers, which are very critical, are cladding and core. And once again, as we move along in this chapter, I will talk more about. We will get to talk more about how they work together. So, in this case, you have a cladding and core. The way they talk together, which will allow light to carry over the cable. The process is called optical transmitter. So if you, whenever you get a chance, those of you who have explored the fiber cable, but when you plug in the fiber cable from one end to the other end, and or just look inside the fiber cable, you will see kind of like a light probe that's constantly coming out from the cable. Of course, it's ones and zeros. So every time you see a light, it's one, and every time there's no light, it's zero. But but you will see a red light coming out from a fiber cable. Something that's pretty cool to look at. But going further on how the inner cores work, which is your cladding and core, and please do remember these components of what makes a fiber cable, because this will be on the exam for sure, because this was on CCT and CSET. So looking into deeper into the core components of fiber cable, what makes them work. So you have on the top you have your multi-mode, and in the bottom you have your single mode. And once again, those of you who are pretty new to the to the fiber cabling, is that there are two different types of fiber cables. One is the multi-mode, and the other one is the single mode fiber. And sometimes they are used as an MMF, and the other ones are used as a SMF. And multi-mode, your cladding and core is bigger than what you have on single mode fiber. So your multi-mode has a bigger diameter, but at the same time, your multi-mode is used for shorter distance, and your single mode has a smaller diameter for longer distance. So just it's just a physics and science behind it, right? The longer the cable, the harder it is to send the data, right? It needs, usually what we have seen is that if you go long, let's say if you install a copper that's like 10 kilometers long, that signal is gonna fade away the longer it takes to get there. So in this case, if you look at the diameters, or let's just take a step back really quick. The way it works is that the light goes to the core, right? But it reflects. Once again, it reflects of a cladding. That's why they two work together, and they're the critical part of a fiber cable. So in this case, when you have a bigger diameter for shorter distance, the light has to bounce off several times, right? It has to bounce off like several times to get there. It's fine. It's fine for short distance, but when you have a longer distance, you can't afford to light to bounce up, because that light is gonna fade away when it comes to longer distances. That's why you need a smaller core where light can just bounce off like pretty quickly, right? Without taking too much time. So so those are the key differences going into the single mode and multi-mode fiber. Please do remember that in the exam, and it will come up on your exam for sure. So, and just experience that I had during my internship is that uh, the fiber cables are more fragile than copper cables. So you cannot just twist these cables back and forth, because you will end up damaging the core. And once you damage the core, the light couldn't get through it. So what I did is, while I was going through cable management throughout my internship, I ended up twisting fiber cable too much, and I damaged the core. And that was a couple years ago. But at that time, fiber was. I mean, today fiber is still expensive, but a couple years ago, fibers were still pretty more. They were more expensive than what they were today. So please do keep in mind that when you are using fiber cables, just be very cautious on how you're using them. Right, on the right side, it's just a logical connection, kind of like what we saw over 10 base and 1000 base T, right? Is that one end will transmit, the other one will receive, and the same thing going to the other way is that the receiver end will transmit on the other pin, and um the sender will transmit on the other pin, and the receiver will receive on the other end. So pretty basic, not too complicated, as your 10 base, 100 base, and 1000 base T, where they use two pairs and four pairs. So it's pretty straightforward. But this is something that's very important going into the exam, because they will test you on this. They will test you on fiber cabling. All right. Uh, let's. I'll be looking at the time. Okay, pretty good. Okay, so as we talk about SFP connections on the top, let me just scroll up really quick. Um, okay, so while we're talking about small form pluggable connections earlier, your SFP plus module only work with 10 gig connection. And those of you remember what I said earlier is that when you buy a SFP plus module, right, for your 10 gig connections, you need to know what standard you want because not all of them are compatible with all these standards. And you're like, hey, what do you mean by that? Now let me scroll down. But before I scroll down, remember we went over some different standards depending on the speed and depending on the requirements. Now it also applies for 10 gig connections. So if we scroll down to 10 gig, let me scroll down to 10 gig. I'll make sure this does not get into your face. But there you go. Okay, so for the 10 gig connections, there are different standards that IEEE came up with. So your 10 gig so once again, it's not just as SFP module, it's also as a network engineer, when you implement when you have a 10 gig connections going from one side to the other side, you need to remember this, the standards and limitations that come with it. So you have your 10 gig connection, 10G base S, which uses multi-mode fiber, and once again, multi-mode fiber is the one that has a bigger diameter and shorter distance, has a maximum distance of 400 meters. Then you have a 10 gig base LX4, which is multi-mode, uses 300 meters. Then you have your 10 gig base LR, which uses single mode. And once again, single mode is the one with the thinner core or with a smaller diameter. What you like can travel much faster than having a bigger diameter, right? Do remember that the key differences, and once again, it makes sense, right? Just look at the distances. With single mode, you can achieve up to 10 kilometers at using the standard LR, and then you use 10 gig base E single mode, which is 30 kilometers. And the way that I remember going to the exam is because this is something that helps me understand going in the exam. I like cars, so I kind of use that as a reference. Um, if they ever end up asking me this question in the exam, is that if you have a S, so 10G base S, I'll use S as a sport, which is 400 meters. Your LX is kind of like a base version, which uses only 300 meters. Then LR, it could be a Type R or like a long range, which is 10 kilometers, and you have electric, which is 30 kilometers. So it just helps me going into the exam, um, uh, just kind of like memorizing um, the distances, and of course, makes it easier going into the exam. All right, moving further, we're gonna talk about frame. And your frame, every time I bring a frame, it's gonna be your data link layer, which is gonna be your layer 2. So when you look at a frame, your frame has a header and a trailer. And once again, your header and trailer are also called PDUs, and PDUs stand for Protocol Data Unit. And this is something that will help us understand how on physical layer, right, your ones and zeros get transitioned over to layer 2, and this will help us understand OSI layer, especially layer 2, more in depth. So what your typical so if any of you guys are using Cisco Packet Tracer, or you can use Wireshark to capture packets in your network, um, you will see what the packets will look like at layer 2, or you will see what the frame will look like. So in this case, when you capture a frame, you have your header and your trailer, and in the middle you have your data. So in header, you have the first byte is your preamble, then you have your SFD, of course your destination and source, your type. Your type is basically IPv4, IPv6. Then you have your data and padding. So your data minimum will be 46 and maximum will be 1500 bytes. Then you have your FCS, which stands for frame check sequence, for error detection, not error recovery, error detection. So just taking this table, learning about different fields. So your preamble is synchronization. Your SFD stands for start frame delimiter. Then you have a destination source. Then you have a type, which is IPv4, IPv6. Then you have your data and padding. So your data minimum is 46, maximum is 1500 bytes. Your frame check sequence, which is kind of like which is kind of like a math algorithm that he uses, so that it looks for any errors. Kind of like your the way that I remember, it's kind of like the integrity check, kind of like your MD5. Or those of you who don't know what MD5 or like hash check is that if you go on a website, they ask you to select pictures or type in a text to make sure you're not a robot. It's kind of like that, but it uses math behind it. So let's say throughout the network, someone uh you know someone attempted to make like a fake frame, or someone hijacked the frame with their own data. What it will do is when it runs this frame check sequence, and if the number does not add up, what it will do is it will discard the packet for error detection. It's not error recovery because once it discards the packet, um, it won't ask for retransmission. So basically, it will just drop the packet if it detects errors, but it won't ask for it won't ask like, hey, send it back. It does not do that because that's not his job. That's transpolator's job for recovery process. But this one only does error detection. And just a quick terms that I have on the right side is that your 1 byte equals 8 bits, and your terms are MTU, which stands for maximum transmission unit. Maximum transmission unit is 1500 bytes, and then you have your FCS, which is frame check sequence. That's error detection, not error recovery. And your type is usually IPv4 or IPv6. All right, going into the MAC addresses. They're also part of layer 2, and this is one of the things that we'll review and you'll be asked on going into the exam. So your MAC addresses are basically kind of like a serial number, right, of your device. That's how you will identify them in your network environment. So the way the structure of the MAC addresses work is there are total 48 bits, and they're divided into now if you look at dive deeper to inspect the MAC address, your first 24 are OUI, which are organizationally unique identifier, and the other 24 are vendor assigned, and they're hexadecimals. So your OUI once again stands for organizationally unique identifier, which is 24 bits. So the way the process works, and I have it highlighted, is that before a manufacturer can build Ethernet products, so anything that has a NIC in it. So anytime, let's say, an Apple comes up with a new MacBook or like an iPhone that has Ethernet in it, it must ask the IEEE to assign a manufacturer universal code. It's kind of like a universal address that they will get assigned to, which is a 3-bit code, which is called organizationally unique identifier. Which means that when you do like an audit in your network environment, you can identify what vendors that they're using. So in this case, it might be Apple or Nintendo or a Switch. Nintendo, I don't know, or your HP devices. You can look at the MAC addresses, and the way you can tell is just by looking at it's just by looking at the first 24 bits, which are universally assigned. Pretty straightforward. Now, diving deep into different types of addresses. As Once again, as I was going through as we're going through the review checklist, right? There are different types of addresses. You have your MAC address, which is kind of like your physical address. Kind of like a serial number. And then you have and then you have then you have like a different names, right, that goes with MAC address. Then you have your MAC address, your Ethernet address, your NIC address, and your LAN address. They're essentially the same thing. You have your burned in address, which is also the short form is like BIA, which is like a 6-bit address assigned by a vendor making the card. It's kind of like they're physically assigned to it. Your unicast address is basically a one address. Uni means one, and then you have a broadcast address, which means like an address that means all devices that reside on this LAN right now. So a broadcast address, the way that I look at it is let's look at the topology on the top, and I'm just gonna take a step back really quick. So, and in this case, the broadcast address, what it means by that is like, hey, I want you to send this message to a whole group in that specific LAN. So in this case, the switch will send a broadcast address to all the devices that are in this LAN connection. So broadcast is basically to a group. Then you have a multicast address. Let me scroll down really quick. Oh, there it is. Your multicast address, basically, it is a subset of all the devices. So, the way I remember is that multicast address is similar to broadcast address, but whoever's first on the group will get to will receive and process the frame first. So once again, multicast address, it is a subset. It implies some subset of all devices currently on the Ethernet LAN. Right. Just a quick review from what we went over from the table on the left. Let me just say. Let me zoom out. Is that your burned in address? Is basically your it's burned into your chip, kind of like your serial number. And then you have your universal address, which is assigned to your NIC, and it's unique. Then you have a broadcast, which is like all F. Then you have your multicast address, which is your sends you a subset of devices. Volunteers in that group will receive the frame first, and they get to process it. And also, this is important, and this is something that I didn't know earlier, is that group addresses. And I got confused by this, but I got confused by the term because I was going through some practice exam questions, and I was like, what is a group address, right? Basically, Cisco likes to call group address as a multicast and a broadcast because if you look at the underlying technology, the way it works is that it sends the frame or a packet or sends the data to a specific group, right? Because your broadcast sends to a group in that LAN. Your multicast address sends to a subset of group, so like a specific group, and whoever gets it first gets to process and gets data and gets to process it. So it makes sense why they call it as a group address. But please do keep in mind going into the CCN exam is that they will test you on this. All right, let's just take a step back really quick. Um, we talked about frame, right? We talked about different fields inside a frame. So once again, just taking a step back, is that it has a header, it has a trailer. But in the header, there's a type, right? That type just tells layer two going into layer the packet going to layer three if it's IPv4 or IPv6. So it in the type, because since we deal with a lot of hex and bits, um, it's not just in computer world. You can't just it's not gonna have IPv4 and IPv6 in the field type. So there has to be a specific way that it knows it's IPv4, IPv6, and the solution to that one is that let me pull it off right here. So assume that this is your frame. You have your header, you have your chiller, then you have your data in the middle, and your type. The way it knows the type is that if it has 0800, it knows it's IPv4. If it has 86DD, which means that it's IPv6. So that's how it will know if it's IPv4, IPv6. It does not say IPv4, IPv6. It actually uses bits and hex and decimals to know. Sorry, yeah, hex and decimals to know the differences. So once again, if you can do this in Cisco Packet Tracer, or you can use Wireshark to capture your packets, and when you go frame by frame, you'll see that type will be defined by 0800 or the 86DD. All right, last but not least, this is really important to understand. Your hub, difference between a hub and a switch, and why hub is no longer used and it's outdated, is because hub, it is a half duplex. And what I mean by half duplex, think of it as a one lane. Just by looking at this picture between Larry and a hub, is that there's only one lane, which means that you can do simultaneous data flow or connections. So which means you can either just transmit, or you either just receive in one direction. You can just do both. You can do both at a time. Whereas in a switch, you have kind of like you have like a two lanes where you can where you kind of think of as a difference between a one way and a two-way street. So if you have a one way, you can only go in one direction at a time. Whereas in a two-way street, you can actually have traffic going in one direction and traffic going on to the other direction. So you can transmit, and also you can receive, because you have two lanes going in both directions. Whereas in the hub, you can only do one direction at a time. That's kind of like a basic way to uh, uh, understand how half duplex and hub works. So half duplex, the device must wait to send if it's currently using a frame. In other words, it cannot send and receive at the same time. So you might be wondering, what happens if it sends and receives at the same time? Now think about it. If you're in a one-way street, you're going in one direction, and someone that comes from the other direction, uh, there's a collision that will happen, right? So what happens when there's a collision? Now there's a whole algorithm that's in place to avoid that collision to keep happening, and we'll understand that in just a minute. So, uh, going back to this topology on the left side, so now you have a Larry, which is connected to a hub, and on the hub on the other end you have two computers, Archie and Bob. Right, Bob and Larry are always used in IT world to understand the uh, you know for visuals and understanding how the underlying technology works. But in this case, let's say Archie and Bob, they happen to send the packet all at once, right? It sends all, once again, it's sending to the Larry. Let's say Bob sent it to Larry, and now Larry is sending it back to the Bob. But the thing is, Archie sent the packet at the wrong time. So now you have a packet going to the Larry, and Larry sending a packet out in a one way street. That will create a collision. So what's the solution behind it? Let's say if you're using a half duplex in your environment, how can we avoid that from happening? Think about it. Think about in a enterprise location. It's not just one, two, or three devices, right? You have like thousands and thousands of devices that you're connected. So how could you avoid that issue from happening? Well, there's an algorithm that goes behind it. So what's the algorithm that goes behind it? It's called CSMA CD, which stands for Carrier Sense Multiple Access with Collision Detection. Ah, okay. So how does this work? Well, let's see how it works, and make sure that this is going to be a CCNA example. Say CCNA question. So so I have it highlighted and because they do like to test you on this exam, they still want you to know how half duplex works and what are some pros and cons. That's why we don't use half duplex anymore. We use full duplex, but they still want you to know because it is a part of the networking world. So what happens when collision takes place? So step one, a device with a frame, a device with a frame. So let's say Bob with the frame, like let's say the frame 1B, it makes sure that uh, it makes sure it listens to the link to make sure that it's not busy. If it's not busy, it will send the frame. But let's say when Bob was sending the packet to Larry, um, let's say while he was sending the packet to the Larry, and discovered that the collision that happened, right, because of unfortunate timing, because there was an unfortunate timing where Archie also sent the packet, right? So what happens in that case? In that case, and in that case, it will send a jamming signal to all the nodes or to all the devices that are connected. So in this case, when Bob detected, oh wait, there's a jam, there's a collision, what it would do is it will send a signal to all the workstations that are connected to the hub. So to avoid further collisions, right? So if you know that there's a collision that happened in a one-way street, you don't want people to keep coming, right? It's, it's gonna be it's gonna create more chaos. So in this case, what will happen is that it will send jamming signal saying that, hey, back off, right? Back off. Wait, not right now. That's what's going on, right? So first it will send a jamming signal. Then everyone will choose a random time because of unfortunate timing. Because of course, timing is the factor in this place, right? Timing is the factor that created this issue. So in this case, Bob will create a timer. Archie will create a different timer. So let's say Bob is at 10 seconds and Archie's at 20 seconds. Now, 10 seconds, the packet went to Larry and came back to Bob. Now Archie has 20-second wait, right? So, you know, that's not gonna collide with Archie, with Bob, because it has enough time to get back and come over. So everyone will back off and they'll choose a random time and wait before trying again. So once that timer expires, basically what timer is basically CSMA CD. It's kind of like a back off. It's like, hey, back off. It's basically called it is called back off algorithm. There's a reason why it's called back off. It's because they back off and they choose a random time and they'll wait and they'll keep doing it until there's no collision. Because now I'm thinking about possibilities like, okay, it may happen once or twice where they might end up having the same timer. But like if they keep trying several times, they're gonna have a different clock on different ends, and eventually they will transmit. So they will keep doing that until step one, which is it will make sure it's not busy. All right. Going back to my notes. Of course, we talked about half duplex, where it cannot. Let me switch over to the right side, where it cannot send and receive at the same time. Then we talk about and that's what half duplex is, and what full duplex is basically a two-way, right? Where you can go where you have traffic going in one direction, and also you have traffic going to the other direction, rather than just having a one-way street. So uh, the device does not have to wait before sending; it can send and receive at the same time. Your hub, what hub does, it's basically hub. It's basically a dumb device, or basically it is like a repeater where it will send basically every time it receives a frame, it will send out to all devices. So let's say if it receives a frame, it will send out to all of them until it gets to the right person. It's not like a switch where it remembers where to go. It does not have a MAC table, a MAC address table. So switch is a layer 2 device that runs on full duplex. Your half duplex uses algorithm called CSMA CD. Is because your half duplex has a downside of a one-way street, correct? Half duplex, remember, one-way street, because if you have one-way street and if you have people coming from both directions, there's a collision that will happen, and we don't want that. So that's the reason why that it uses an algorithm called CSMA CD, which stands for Carrier Sense Multiple Access with Collision Detection. So please do remember going into the exam that you will be tested upon this, and feel free to feel free to take screenshot of my notes or jot it down, write it down, whatever helps you. All right, that's it for today. I know I covered a lot of things in this chapter, but once again, it's very basic, very foundational, nothing crazy going on. It's not technical. It's just a foundational knowledge that we all need to know before we move further. So we talk about cabling, right? We talk about fiber, straight through and crossover. Then we talk about different LAN with different LAN standards, which are 10, 100, 1,000, and 10 gig connections. So let me mark them off. Then we talk about your MAC address, also known as Ethernet address. Your first 24 bits, last 24 bits. Then we talk about group addresses, your multicast and broadcast. Remember, Cisco calls it as a group addresses because, once again, your multicast address sends to a subset of a group, which means that there's a specific group that will send it out to, and whoever gets whoever gets it first will get to process and receive it. Whereas in broadcast, it will just send out to a group all at once, right? And Unicast, uni means one, basically one to one. Your frame, we're talking about different fields in the frame, right? We talk about preamble, SFD, your source, your destination, your type. Of course, we talk about type, like in type we have IPv4, IPv6. We talk about data, we talk about FCS. Once again, frame, uh, you need to understand the key components in frame. So going back to the chapter 2, please remember going into the exam that your FCS is the one that does error detection, kind of like a integrity check, right? So if it sees any error, it will basically drop the packet. It does not do error recovery; it only does error detection. And also, just to keep in mind, the maximum data that you can send is 1,500 bytes. Minimum is 46. Right, we talk about frame. We talk about SFP modules. Remember those modules that you can attach to your switch? GBIC, gigabit. I'm still having a hard time remembering this name. Gigabit interface converter, something like that. I need to remember what it stands for. It might be a trick question on the exam. But you have your GBIC, you have your SFP plus. GBIC is the kind of like a credit card size, bulky, right? Old bulky connector. That's the very first one that came out, and now no one uses it. SFP and SFP plus, they're more like a flash drive version, right? Right. And last but not least, we talk about half-duplex. Half-duplex is like a one-way street, right? It uses an algorithm called CSMA CD, which stands for Carrier Sense Multiple Access with Collision Detection. Basically, to avoid any collisions. That's what the algorithm's for. And you have a full duplex, which is used by a switch, um, which means that it's kind of like a two-way street, right? You can send and receive at the same time. So basically, that was it for today. We talked, this chapter mainly focused on fundamentals of Ethernet. So of course, layer 1 and layer 2. Moving forward, I'll try to keep this video short, but also I like to go over my notes. And also it's kind of like a review process for me as well, because I get to do this before the video and after, and of course while I'm doing the video as well. So it's kind of a refresh for me. But going into the next chapter, which is chapter 3, we'll be diving deeper into WAN. I know this was more into LAN connections, local area network, but we'll be going over IP stuff. So we're gonna go over layer 3. And we're going to be diving deeper into layer 3. We'll be going over a couple of protocols that we'll end up using, for your WAN connections. So keep that in mind.